And now we want to move forward with Dr. Kawashima. If you can join us on stage. Here he is. Dr. Kawashima, please.
My presentation will focus on one question: why IOWN Global Forum technologies will drive our growth. So let me start with a few highlights of our computing infrastructure. So first, data centers geographic shift. So now major data centers such as North Virginia are expanding with many secondary data center districts. So for example, North Virginia data center district used to be Ashburn, but now the Virginia data center region consists of many more data center districts. And second, new computing ecosystem with tier 2, tier 3 clouds. The cloud used to be dominated by mega clouds, but for AI computing, we will see neo clouds, and also we will see sovereign AI for multiple levels, like national sovereign AI or industrial sovereign AI or enterprise sovereign AI. And the third point is rise of private fiber networks. So because of that, private fiber networking is becoming very attractive for the interconnection of distributed data centers in the region. And the products and services for private fiber networkings are expected to grow. So people are now talking about managed optical fiber network, MOFN, and also IP over DWDM transponders are expected to grow. So cloud providers are building private fiber networks to interconnect their data centers. So could this create the ultimate computing environment? I mean, one environment that empowers nations and businesses to stay competitive with AI while also advancing global sustainability? And the answer is no, because we face two critical challenges. First, the computing environment will be fragmented into optical silos, because today's transport systems cannot achieve efficient or optical interconnection. And the second, enterprises, which are the consumers of such accelerated computing infrastructure, will be left behind because they are isolated by the limits of today's IP1. This is where IOWN Global Forum technologies will come into play. So this is the overview. Here's how we tackle these challenges. Our infrastructure stands on three essential layers, which are optical transport, packet forwarding, and accelerated computing. At the bottom, we have an optical transport layer. And groundbreaking feature of this optical transport layer is capillarization, which means extending optical transport infrastructure beyond large hubs like carriers backbone stations or hyperscalers data centers to small and medium-sized data centers and even to customer sites. And then by leveraging this capillarized optical transport layer, the packet forwarding layer can deliver deterministic quality. And then by leveraging this deterministic packet forwarding, we enable seamless multi-site accelerated computing. So let me explain each layer in details. So let me start with OpenAPN. So OpenAPN achieves optical transport capillarization by breaking down today's optical transport system into modular components and distributing them to provide dense and widespread coverage. Of course, many open infrastructure consortia define disaggregation architecture. However, simply disaggregating systems would not create a big value. Beyond disaggregation, OpenAPN achieves 3 more Ds, which are distribution, demarcation, and digitalization of operation. Distribution is about deploying components across different locations. Demarcation is about allowing different organizations to operate different components or different segments of the infrastructure. And this is important for the operation of such multi-domain infrastructure and for all optical interconnection. The third point is the digitalization of operation. This is about enhancing visibility and enabling AI-driven control. Of course, we don't reinvent the wheel. Instead, we embrace the architectures and open specifications created by other consortia and make them more deployable, more flexible, and more impactful. So in doing so, we amplify their values, so other consortia are eager to collaborate with us. So in the opening plenary of this conference, our panel with Open ROADM and OCP highlighted the importance of our collaboration. Also, from an economic perspective, OpenAPN delivers a major advantage. This advantage comes from 2 key factors. One is the product life cycle of infrastructure nodes. In today's optical transport system, infrastructure nodes consist of both electronic components and optical components. On the other hand, in IOWN APN, infrastructure nodes consist only of optical components. While electronic components must be repeatedly upgraded to keep up with the transceiver standards, optical components remain usable across multiple transceiver generations. That's why all photonic networks enable operators to reduce the infrastructure capex significantly. The second important factor is how the terminals technology upgrade costs show up in infrastructure providers' profit loss statements. Today, transponders are provider assets. That means the provider should recognize their depreciation cost. On the other hand, with IOWN APN, transponders may become customer equipment. That means infrastructure operators may be able to regain terminal user equipment sales revenue instead of recognizing cost. With this new financial structure, infrastructure providers can deliver dense area coverage with lean investment. So with this new optical transport layer, packet forwarding no longer needs to rely on a patchwork of distributed nodes. Instead, we can deliver it as a unified cloud service built on a hub and spoke architecture. We call this concept packet hub and optical spoke. We can summarize the benefit of this novel architecture in 3 letters, DEF: deterministic quality, efficiency, and faster innovation. This is, maybe you can imagine, you can remember how FedEx revolutionized their package delivery business. They introduced tracking service, and they introduced overnight delivery. Like that, we can revolutionize packet forwarding service. So the forum's new document, Deterministic Networking, outlined the key nodes for the packet hub and optical spoke architecture. And now we are planning a proof of concept of this architecture. So the packet forwarding layer with deterministic QoS will transform the relationship between the edge and the cloud. So with today's one, the edge cannot effectively share IT resources with the cloud. By contrast, with open APN and deterministic networking, the edge can access cloud IT resources. This is what we call edge-cloud convergence. But upgrading the network layer alone is not enough to achieve edge-cloud convergence because of two key reasons. First, today's one relies on TCP/IP, which places a heavy load on CPU. And second, nodes cannot interact directly because firewalls stand in the way. That's why IOWN Global Forum defines an architecture for distributed accelerated computing. It enables RDMA across data centers and protects computing nodes with endpoint security installed on smart NICs. So let me recap. We have introduced the capitalized optical transport layer and the deterministic packet forwarding layer and the infrastructure for multi-site accelerated computing. Many people are talking about accelerating computing. People are interested in accelerated computing infrastructure. But most of the discussion outside of this forum is about the computing infrastructure in one data center. But here we are discussing multi-site accelerated computing infrastructure. And we believe this is the key point to enable nations and societies to stay competitive while achieving global sustainability. So in conclusion, here are the key takeaways. The forum has defined the 3 layers: capitalized optical transport, and efficient and deterministic packet forwarding, and multi-site accelerated computing. And the 3 layers combined will connect multiple AI clouds into a single, seamless, accelerated computing space. And it brings the consumers of accelerated computing, I mean enterprises, into the cloud. And APN economics will drive our growth. So that concludes my talk.